All right, so we're going to carry on from our last meeting, and we were looking at the term structure of interest rates. Now, remember that refers to the pattern of interest rates for bonds of different maturities. Normally, this refers to the Treasury market. And so, if you recall, last time we went and looked on the internet, and we looked up the actual numbers for the current Treasury yields. So let's do that right now. God, where is it? Here we go. Okay, so this is the website from the Treasury Department. They publish this every day, and you can see that what they've done is they've listed all the different Treasury securities, and each one is considered to be free of credit risk, but they all have different maturity dates. You can see that in this market, we have maturities everywhere from 1 month to 30 years, which is unusual in most bond markets. There's not that many choices, but the demand is there. There are different market participants who need very short-term investments, and there's some in the middle, some at the long end of the curve. And so you see them all. And so the numbers you see here, these are the yields for the different Treasury securities. And so this pattern of numbers is referred to as the term structure of interest rates. Now, I did mention the other day that the pattern we're seeing here is a bit unusual by historical standards. Usually we start out with very low yields for the short maturity treasuries, and then they gradually work their way up. And in fact, if you were to draw a typical a graph for a typical term structure, you'd end up with something like this. So what you're seeing here is that on the vertical axis, we have the yield. On the horizontal axis, we have the maturity. And then this would be the normal pattern. By the way, this graph is referred to as the yield curve. And it is an illustration of the term structure of interest rates. So let's say that at some point in the past, you would have had a yield of 3% for a 1-year treasury bill. Hold on a second. And then maybe for a 30-year bond, it would have been more like 6%. Okay, and so that would have been a more normal pattern throughout most of the 20th century and the 21st century. This is what you normally expect to see. What you're seeing here is a little different. You see that the yields are fairly high. And in fact, they're even going up a little bit more before they drop off. So what you're seeing now, let's call this the usual. And then what you're seeing now is more kind of like this. And so that often indicates that things aren't going so well in the marketplace. It can mean that, for example, people are nervous about the future. It could mean that people expect rates to fall in the future. It could be that we're in the middle of a recession or that one is expected. It also sometimes happens when we have an unusually high inflation rate. So a curve like that is not the best thing in the world. It's a sign that the markets are nervous, basically. But anyway, as I started to say the other day, we actually have 4 equivalent ways of expressing interest rates. Yields to maturity, which we normally use to price bonds. And we also have spot rates, forward rates, and discount factors. Now, here's the interesting part. They all give us the same ultimate result. In other words, if you price a bond using yields, you'll get the same result if you use spot rates to price that same bond, forward rates, and discount factors. So in that way, they're equivalent to each other, just like 0 degrees Celsius is the same thing as 32 degrees Fahrenheit. It means a freezing point of water any way you look at it. The numbers are different, but it represents the same idea. So something similar is happening here. But it turns out that yields are primarily useful for the bond markets. The other 3 are much more useful for other types of applications. And in fact, we'll spend most of the time using spot rates, forward rates, and sometimes discount factors as well. But the really important ones for our purposes are the spot rates and the forward rates. So the yield to maturity, as I started to say yesterday, is basically the number. Oh, actually, for this, I would like to go back and grab the pricing formula from the previous section. Oops, no, I need the, no, come on, here we go. So this is our very familiar bond pricing. Actually, I don't want it here. Let's put it here. So basically what they're saying here is that on the right, what you're actually seeing here is the present value of the coupons. And over here, you're seeing the present value of the bond's face value. And that adds up to the bond's price. I mean, or think of it as the future present value of all of its future cash flows. Okay. So remember, by definition, the price of a bond is the present value of its future cash flows. So that means the left-hand side and the right-hand side have to match each other. But here's the interesting part. The price over here is an observed market variable. So this is something we can observe in the marketplace. You can look it up in the Wall Street Journal. The yields are implied by this equation. In other words, you cannot look this up in the Wall Street Journal, or if you do, what you're going to see is the result of somebody taking this equation and finding the value of R, which ensures that the right-hand side and the left-hand side match each other. So you can think of the yield as simply the unique interest rate at which the market price of this bond matches up with its present value of its cash flows. And if you look at the price yield curve, you'll see that for any price, there's one and only one. Actually, let's get this out of here. Okay, so for every price, there's one and only one yield. And conversely, for every yield, there's one and only one price. So this is a one-to-one function. P of R is a one-to-one function. Now, unfortunately, though, even though we know from previous math classes that if a function is one-to-one, that guarantees that it has an inverse. Here, it's not normally possible to find that inverse. Because of the way the formula works, there's actually a result called Descartes' rule, where it basically tells us that for a function like this, if we have, let's say, 5 cash flows to this bond, it becomes mathematically impossible to invert this function. And even with fewer cash flows, it's quite difficult. So the normal procedure is to not try to solve for R directly, but to search for R using numerical techniques where we basically try to find, we try different values of R until we find the one that works. And so that's why that has to be done with a computer rather than a calculator, because otherwise it could take the rest of your life to get it done. So we're going to actually fairly soon visit that discussion from chapter 1 about Newton's method, which will enable us to do exactly this. At that time, of course, we're going to have to wait until we start going over VBA, but we will do this very soon. Anyway, now the yield to maturity to an investor can be thought of as approximately the rate of return that you'll earn from holding this bond, but that assumes there's very strong assumptions involved here. In other words, this will be true only if, number one, you hold the bond to the maturity date, which means you're guaranteed to receive the face value at maturity. And number two, if all those coupons that you receive are reinvested, and not just reinvested, but earn the yield to maturity as their rate of return. So in other words, if, let's say, why don't we think about it this way? What could cause the rate of return to deviate from the yield to maturity? Well, number one, if the bond is not held to maturity, the price at which it is sold can be greater than, less than, or equal to the face value. Now, if it's different than the face value, that's of course going to affect your rate of return. All right, so the yield to maturity is assuming that you're holding it to maturity and receiving the face value. And number two, if the coupons are reinvested, or let's just say coupons can be reinvested at a rate that is greater than, less than, or equal to the yield to maturity. And of course, that will also affect our rate of return. So we could get a higher return than is suggested by the yield to maturity. We could get a lower return, or it could exactly match the yield to maturity, although that doesn't happen very often. So unless something goes terribly wrong, the actual return should be pretty close to the yield to maturity, but it probably won't be identical. So it's only approximately equal to the rate of return to owning that bond. Okay, now what about these other three alternative types of interest rates that we might encounter? Well, the next one is the spot rate. The spot rate, we really think of it as the yield to maturity of a zero coupon bond. Now we know that a zero coupon bond does not pay any coupons, of course. Instead, it is sold at a discount from the face value and then redeemed at the full face value, providing the investor with a capital gain. For example, suppose that a 1-year treasury bill is sold at $9.50 and redeemed at $1,000. The yield or return is, so in the numerator you have the capital gain 50, and all that is divided by the purchase price of $9.50. And that equals, let's see, hold on. It's 5.26%. Now, here's the thing though, because there's no coupons and because it's being redeemed at the full face value, the yield and the return are going to match each other unless, again, you sell it prior to the maturity date. So as long as you hold this bond to maturity, since there's no coupons to reinvest, that's the only requirement for the yield to match the rate of return. If you hold it for the full year, you're guaranteed to get a rate of return of 5.26%. And that makes things a lot easier for investors. The only unfortunate thing is that these zeros only go out for a full year in the treasury market. So, what do you do if you want something else? Well, it just so happens that there do exist products that are designed to get around this little problem. I'll just mention this briefly here. Suppose now, so zero coupon bonds are only available in the treasury market for maturities up to 1 year. By the way, in the corporate bond market, you're not going to find this because they're always coupon bearing bonds. They simply don't have zeros for corporate bonds. But and even in the treasury market, it's only up to a year. So here's the interesting part. Now, on Wall Street, they make their money by providing investors with products that they want. So here's what can happen. In the, let's say 1985 or so, it became clear that there was a demand for zero coupon bonds with longer maturities. So what happened was Wall Street firms, and we could look up the ones who started this. I don't remember exactly who got this idea first, but came up with the idea of buying a portfolio of treasury securities and then selling the coupons to their clients at a discounted price. Now, how would that work? All right, let's try this. For example, suppose that Wall Street owns a treasury bond that will make a $1,000 coupon payment in 10 years. The firm can sell this coupon to a client for a discounted price. And for 10-year, let's just say that the price would be, we just make up a number. All right, I'll use a real calculator. I don't know why my phone calculator suddenly decided not to work anymore. That's the way technology is. It's always going to let you down at the most important moment. All right. So hold on 1 second. Let's say the yield is 5%. The price would be 613.91 of 91, and then redeemed for $1,000 in 10 years. So now here's the interesting part. This is really the most important detail. When the Wall Street firm owns this dealer, this would be, by the way, this would be a government bond dealer. Not everybody is allowed to deal in treasuries. Certain Wall Street firms, the big investment banks, can be designated as a government bond dealer, which gives them the right to directly buy and sell treasury bonds with the government. In other words, they're not just buying and selling their own inventory, but they can directly deal with the government. And so what happens here is that this bond that they own with the $1,000 coupon the government has a record of this somewhere. They sold it directly to this Wall Street firm. So the bottom line here is that if they sell this coupon to a customer and then they go out of business, the customer will still get the $1,000 because there's a record of it somewhere. The government knows that that coupon is meant for this customer, and so there's no credit risk. Okay, in spite of the fact that the Wall Street firm is involved with this process, um, they're guaranteed to get the $1,000. So in other words, it doesn't really matter to them that this bond is being artificially created by this Wall Street firm. It's still, as far as they're concerned, is a zero coupon bond that sells today for $613.91 and will be redeemed for $1,000 in 10 years, guaranteed. So from their perspective, it's the equivalent of the Treasury issuing a 10-year zero coupon bond in the first place. So what we have here, this is a synthetic 10-year Treasury note, which is known as a strip. Now, this strip is an acronym. I have to look it up, the exact letters. It's separate Treasury something or other. Let's go look it up real fast, the exact wording there. Separate trading of registered interest in principal securities. Okay, so this was done to give more flexibility to investors who really do want these long-term zero coupon bonds. Now, you can imagine that they have some appeal in the sense that you're guaranteed a certain rate of return in the future. You don't have any coupons to reinvest. And that's very attractive to some investors. If you know for a fact you won't need this money for 10 years, then this might be the way to go. But at the same time, though, you don't get those intermediate coupon payments. And I know that there are some tax implications. I don't think it's the case that you can simply wait 10 years to pay the taxes on the capital gains. I think you have to pay some of it every year, but I don't know enough about that. But anyway, for the investors who do want these, they're very popular, by the way. The volume of trading in these things is quite large. I don't, like I said, whoever came up with this idea, hopefully they made a lot of money because it's a huge market. So like it says here, the government does not actually issue strips. That they instead they let the government bond dealers take care of this. So we have financial institutions such as investment banks who purchase conventional treasuries and strip the interest away to be sold to investors as separate securities with CUSIP numbers. I mean, that's a unique identifier that every bond has a CUSIP number. They're backed by the full faith and credit of the government. In other words, you don't have to worry about this financial institution failing you, because otherwise they're not risk-free anymore. And then what's the point? So yes, that is the important part, the fact that no matter what happens, you'll get your money. Okay. So like it says here, we've got a bank that registers and sells each interest payment separately to different clients. So it's a pretty brilliant idea. And I don't know if we can look up the volume of trading in this market. By the way, here's a really bizarre feature. The brokerage house who initially sold off all these strips, they can buy them back and turn them into a full coupon bond and sell it as a bond again. They can, so it can be split apart and they could be put back together again, just like Legos. Yeah, I thought that maybe we could find a dollar amount, but It's a large number. It's a very, very popular market. Now, interestingly enough, as we'll see in a few minutes when we get to the discount factors, the prices of strips are quoted as discount factors. And in other words, what you want to know is what percentage of the face value are you actually paying for it. So here, for example, the price is $613.91, but this price would have been quoted as 0.61391, meaning 61.391 cents on the dollar. Okay, that way the price is not affected by the face value. All right, anyway, so the strips are an example of zero coupon bonds, but they had to be artificially created by Wall Street firms because they did not exist in the marketplace. And so these are known as synthetic securities when they are created artificially from the cash flows of existing securities. Okay, you see a lot of this in the derivatives markets. We take cash flows from all over the place and turn them into alternative products that are more desired by investors. All right. So now here is an example. Here's a one-year Treasury security, face value of 1,000, sold at a discounted price of $952.38. That implies a yield of 5%. Now, by the way, how do you know that? Because let's quickly do the math. You take 1,000 minus 952.38 divided by 952.38. You'll see that you have a capital gain of 47.62, and you invested 952.38, and that gives us exactly 5%, within rounding. Okay, that's our yield. Okay, great. Now, we also see in the marketplace, though, a two-year treasury. By the way, the one-year treasury is called a treasury bill. The two-year treasury is called a treasury note. This one is a coupon-bearing bond. It has annual coupon payments of $55 and a face value of $1,000. Now, because the bond is selling for $1,000, the yield to maturity is 5.5%. Okay, so I just want to mention that right now. One of the interesting features about the bond market is that if a bond's price equals face value, the yield to maturity equals coupon rate. If the bond's price is greater than the face value, yield to maturity is less than. Now, why do you suppose that is? Because when you buy that bond, you're paying more than $1,000, but at the end, you're only getting $1,000 back. So that means you're going to eventually suffer a capital loss, which reduces the yield of the bond. Okay, so, and then of course we have the third possibility. Let's throw that in here. Oops, it's not what I was expecting. If the bond's price, of course, is less than face value, the yield to maturity is greater than the coupon. Meaning that you buy it for, let's say, $980 and you are redeemed at $1,000, you've got a $20 capital gain mixed in with your coupon payments, and that raises your yield to maturity. Okay, so but in this case, we're assuming that the price is exactly $1,000. So the coupon rate and the yield match each other. Okay. Now, there's a 3-year treasury note that's making annual coupons of $60, meaning a 6% coupon rate. Therefore, because the face value and the price are 1,000, the yield is 6%. So here's the chart. Now, I'm going to try to copy this into Excel. Ooh. All right, that should do it. It's still much. There we go. Okay, so in other words, you look in that website we were looking at before, and this is what you're seeing. The 1-year yield in the treasury market is 5%, the 2-year yield is 5.5%, and the 3-year yield is 6%. Okay, so what are we going to do with this information? Well, what we're trying to do is figure out the corresponding spot rates. Okay, now it turns out that since, I'll mention this down here, since the 1-year treasury bill is a 0 coupon bond, or does not pay any coupon, let's put it that way, and is sold at a discount from face value, the yield and the spot rate will match each other. That's because we formally defined, remember, a spot rate as the yield to maturity of a 0 coupon bond. Therefore, this first one is easy. It's just 5%. The next two, well, that's a lot trickier. How do we get those numbers? Well, first of all, this is how we calculate the price of a 1-year 0. Now, if you notice, the notation has changed a little bit. We're going to use the letter S here to represent a spot rate. So S of T is the T-year spot rate. So we're discounting the face value because that's the only cash flow by 1 plus the spot rate, and that gives us the price of the bond. So what happens here is that the price, remember, we said that this is a discount instrument. It sells for $952.38. The face value is 1,000, which implies a yield of 5%. And based on the logic I showed you earlier, we can rearrange this algebraically and discover that the spot rate, which equals the yield, 5%. Okay, now what about the 2-year spot rate? Good question. Now, here's what's happening. This one has coupons. It lasts for 2 years, which means there will be 2 coupon payments, one at the end of year 1 and one at the end of year 2. And in year 2, you also get your face value. So now here's the other thing that's extremely important. If this was if we were pricing this bond with yields, these are both the same number. It's a constant across the board. But here, we can have a different value of S1 and S2. That's one of the major differences between spot rates and yields. With yields, we're discounting all the cash flows with the same yield to maturity. With the spot rates, each cash flow gets its own unique spot rate. And that's one of the reasons why it is important, except for bond pricing, this is more commonly used because you're giving each cash flow a discount based on that maturity date and nothing else. Whereas here, this R is a weighted average of the spot rates. Okay, it's a single number that reflects all of the spot rates, and it's used across the board for all of the cash flows, whereas here, each one is unique. Okay, now here's the thing. How do we solve for this? Well, we actually have all this information except for S2. If you recall, we were told that the 2-year treasury note has a coupon of $55. We have a face value of 1,000 rather. And we already determined previously that the yield of the spot rate for 1 year is 5%. So if you notice, the only thing that's missing is S2. And so that means that we can rearrange this algebraically and solve for S2, and it's 5.514%. Now, of course, we're going to, the third spot rate, we're going to do something very similar. Okay, so we have to now write out, yes, there it is, the pricing function for 3 cash flows. And except this time we're using, of course, spot rates instead of yields. Whereas with yields, it would have been the 3-year yield applied to each of these. Whoops. And again, all those 3 R's that's the 3-year yield. It's the same across the board. Whereas down here, we have a cash flow or spot rate rather for each one. And so once again, when we plug in the numbers, we realize that we have all these numbers except S3. We calculated previously these two. And so all that's missing is S3. So now we just do a little algebra and we can solve for S3. 6.041%. Interesting. Now, and like I said, what's important about this is that if I had a 3-year bond, let's say, let me just make up an example of this real fast. A 3-year bond has a coupon rate. And this is actually, this is the treasury market. So let's say this is a 3-year treasury note. It has a face value of $1,000 and a coupon rate of 6%. If the coupon rate is 6%, that implies $6 times $1,000, which is 60. Now, by the way, if you notice, we're doing this with annual cash flows just to keep it simple. What is the market price of this bond? Well, we can answer that question in 2 equivalent ways. Okay, so what we're going to do is create a chart. 3 years, 3 cash flows. So first, we're going to calculate the present value using yields. And then we'll do the same thing with spot rates. Okay, so it'll be interesting to see what happens here. All right. So based on the chart, we have, oh, by the way, so that means the cash flows are 60, 60, and 10, 60. Based on the yields, so because it's a 3-year bond, we're going to use the 3-year yield. I'll make a note here for that. Since this is a 3-year bond, the price is determined with the 3-year yield. Okay, if you choose to price it with yields, use the 3-year bond. So you're going to have the cash flow divided by 1 plus. The 3-year yield is 6%. That's cell B4. And the exponent is the year in which I received the cash flow. All right. And I don't need all those digits. Actually, yeah, get this. So I'm going to add those up, and that's going to be my price. $1,000. Now, using the spot rates, I should be a little careful. We have this number divided by 1 plus 1-year spot rate raised to the first power. Now, because the table, I want the rates to change. Here I did not. The yield is a constant. But here it will change. So in other words, when I go to the next row, I want the 2-year yield and then I'm sorry, the 2-year spot rate and then the 3-year spot rate. So I can just drag this down. And even though they're different from each other, they're going to add up to the same thing. So you notice how all 3 of them, they're different, but yet they add up to $1,000. So that's how we know, by the way, that these spot rates were calculated correctly. If not, we would see a discrepancy between the price of the bond using yields and spot rates. So that's also how I know there's the equivalent information to this information. But for most purposes, we'll see, these are easier to work with than these. Yes, spot rates will prove to be hugely important as we go along. We'll use them almost all the time. Like I said, we'll only stick with the yields with the bond markets. Now, by the way, normally you're taking yields from the treasury market and you're converting them to spot rates. But you could, in principle, work this backwards. If you were given a set of spot rates, you theoretically could turn them back into yields with this formula. And, you know, it seems like, why are we even bothering to do this? But you never know when it might come in handy. But in practice, you're usually starting with yields and turning them to spot rates because that's how the market is determined. All the trading is done based on yields. And so the spot rates have to be backed out of the yields. So here, you know, we don't want to spend a lot of time with this, but you can see if you substitute these numbers in, it does work. Okay. Now, forward rates. This is a very, very tricky area. It's going to take some getting used to think about forward rates because we don't normally observe them in the marketplace. They're implied by the pattern of spot rates. So just to introduce this, a bank pays a 5% rate of interest for 1-year time deposits and 6% for 2-year time deposits. Let's say that they are willing to give you a higher interest payment for the 2-year deposits because they can lend it out and make more money that way. And if you've ever gone into a bank and you look at the interest rates that they're paying, there is a product which you may have heard about. Let me just slip this in here. Everybody knows what a savings account is, but banks offer a special type of savings account known as a certificate of deposit, or simply CD, where the investor must keep his or her funds in the bank for a fixed length of time. For example, 5 years, but also earns a higher rate of interest as a result. So in other words, and I don't know if we can actually look up CD rates on the internet. Yeah, I mean, if you went into a bank, your bank, you might see, for example, a bank pays 3% on savings deposits, 3.1% on its 1-year CDs, I don't know, 3.3% for its 5-year CDs, and 3.5% for its 10-year CDs. You can see the pattern there that is emerging. They're able to give you more interest because, let's say you've got a 10-year CD, that's money that you won't be able to touch for 10 years. So they can feel free to lend it out to somebody for their mortgage and earn a very significant amount of interest themselves. So they can pass that along to you. So yeah, next time you're in a bank, go ahead and look and see what they're offering. It's all written up. There's somewhere on the wall where they have a list of all the interest rates that they're paying. So let's just say now this is an extreme case to jump from 5% for 1 year to 6% for 2 years, but all right, you get the idea. So imagine yourself putting your money in the 2-year CD or time deposit. After 2 years, the future value of that sum is $11,2360. Okay, fine. But what if you did the following? You put your $1,000 in a 1-year time deposit, and when it matures, you roll it over into another 1-year time deposit. So it's still a 2-year investment, but you're starting again at the end of the first year. You lock in a 5% rate of return, and then whatever amount you have in your account, you stick it in the bank for another year at whatever rates are available at that time. So this is what you'll have. This is your future value, and you notice X is the variable. What's missing here is what rate are we earning during the second year? So it turns out that if during the second year you earn 7.01%, in both cases, you'll end up in 2 years with 11,2360. So you see how we solved for it algebraically. This is the future value of investing for 2 years at 6%. This is the amount you'll get if you invest for 1 year at 5%, and then for another year at an unknown percent. Algebraically, this is 7.01%. So if you were offered the opportunity to invest for 2 years at 6%, or 5% for 1 year, followed by 7.01% in the second year, you would be indifferent between the two. This number is known, therefore, as a forward rate because it equalizes the returns to the 1-year investment and the 2-year investment. The 2-year investment and the 1-year investment rolled over for another year. So we're going to call that F1, 2, meaning this X is the rate that starts in year one and matures in year 2. So this is going to take a little getting used to, because normally with an interest rate, you figure the rate starts today and it matures at some point in the future. Here we've got 2 time dimensions. When does the rate start and when does it mature? So that's little t means when does it start, and this capital T is when does it mature. So this X would be therefore defined as F1, 2. And in English, we call that the 1-year forward rate 1 year forward. So in other words, you have to specify when does it start and when does it mature. Now, you can have in principle, any forward rates you can imagine. Like you can have F2, 3 starts in 2 years, matures in 3 years, or F1, 3 starts in 1 year and matures in 3 years. Okay. So what we want to do is figure out how to calculate forward rates based on the spot rates that we already have. So the one we just did is this example right here. Okay, so remember, we just got through showing that these give us the same future value. Okay, so in general, we can always solve for. Now, if you rearrange this algebraically, what you'll see is, oh, and by the way, this is the example we were working on earlier. If you rearrange this algebraically, you'll see that oh, sorry, hold on. Let me and then you can solve it from there. So what they want us to do now is take this and bring it back to our spreadsheet. And do the same thing. Now, by the way, if you notice, remember before we said that the spot rate for 1 year is the same as yield because this is a zero coupon bond. The way forward rates work is that this rate here is technically what we would call 0, 1, which is just the spot rate. Because it starts today and ends in 1 year. So this by definition is a spot rate. So we don't have to do anything here. It's just the same. This is the tricky one. So I'm going to copy this here so we can keep an eye on it. So we'll do this in Excel. 1 plus this number squared over 1 plus spot rate here minus 1 . Oh. And then, so what does that suggest about this one? Now this, oh, and don't forget, this is F1, 2. And that makes this F2, . So let's go get the formula for that. Formulas. So what's happening here is that this would be equivalent of saying, well, if I keep my money in a 2-year CD and then roll it over for 1 year, I need to know what rate would be necessary to match up with getting a 3-year CD. Okay, in other words, this is what equalizes 2 years rolled over for a year or 3 years. What rate in the third year equalizes the two rates of return? That's what this spot rate means. This forward rate means. So you're going to have 1 plus the 3-year spot rate cubed over 1 plus the 2-year spot rate squared, all minus 1. And there it is. Now, we would like to confirm this. But pricing with forward rates is a little bit different than pricing with yields or spot rates. Okay. So that's going to be a little bit trickier. Let's see. And here's the general formula for forward rates. Yeah, this, you see what I mean? Look at this. Oh my God. To get a spot rate from the forward rates, look at that formula. So let me just pencil this in here for a second. For 1 year 0, the price will be I can replace the spot rate with F because it's the same thing. But for 2 years, it gets just a little messy. Ooh. And then for the 3-year bond, oops, sorry, no, I completely did here. Wow, it's getting really messy, but we're going to see that it produces the same results. So here we'll have the cash flow divided by 1 plus F01. Fine. So these two are the same. They should be. But here we're going to need the 2-year cash flow divided by 1 plus. No, we'll start with the 1 year. Sorry. Yeah, we'll start with the 1 year. No, sorry. Yeah, this will be 1 plus the F01 times 1 plus F12. We have to put all that in parentheses. Oh, what did I do? Oh, I forgot to multiply it. No, this should have been B20. No. Oh no, these, what am I doing? This is D, this should be D2 and D3. I don't know what I was doing there. That's much more like it. And then for this last one, we're gonna need the product of 1 plus F01, 1 plus F12, 1 plus F23. Now, if you notice this time, not only is the sum the same as for the other two, but the present values are the same. In other words, these are all equal to each other. And that's because the forward rates are derived directly from the spot rates. So not only are these all the same, but these two, the actual year by year cash flows are the same as well. Okay. Now you're probably wondering, what in the world are we going to do with forward rates? Well, you'll see. It'll take a while before we get to that point, but we will definitely do this. In the meantime, the spot rates will be pretty much the way to go, but we still have to cover the discount factors. Now, those are a lot quicker and easier. And like I was saying before, they are used to price strips in the strips market. So I think we can save this for next time. And then once this is done, we're going to start looking at VBA and start to learn how to use it. Where is it found? How do you execute it? And then we can start some basic examples, and then at some point start working on assignments. All right, so I think this is enough for now. So next time we'll wrap it up with discount factors and some important details about these, and then we can sort of do a detour into VBA. All right, so I'll see you next time.